Hello everyone, my name is Maximilian Bruch. I work for the Fraunhofer Institute for Solar Energy Systems, and today I want to talk to you about the project JOSPEL and the battery system we develop in this project. So first of all, I want to introduce my team, Battery Engineering. Then I want to talk about the battery system we design in JOSPEL, lithium-ion battery cells in general, battery system design, state of charge estimation, battery longevity, thermal modeling, and battery management. So the Fraunhofer Institute for Solar Energy Systems is the largest research institute for solar energy in Europe, with over 1,000 employees and the main center in Freiburg, Germany, and also two others in the US and Chile. My team, Battery Engineering, basically focus on also using the solar energy when the sun is not shining or when you want to use the energy in your car, for example. So we test a lot of batteries. We test small cells, modules, and whole systems. So we can even start with small coin batteries we build ourselves to test different materials, but we can also test whole systems like residential storage systems you can use to store the energy from your PV system. We also make models to estimate the state of charge and the state of health of the batteries. We make our own battery management systems. We optimize the lifetime and the thermal properties of the systems. We do quality assurance for PV power plants that also have battery storage. We optimize and do the operational management for battery systems, and we evaluate and check safety concepts for battery systems. So therefore, we need a lot of battery testers, like small ones for small cells, big ones for bigger cells, and we also have one big test bench for testing whole systems with high power. We also have different climate chambers, which we use for testing at set temperatures, and the calorimeter for testing the heat dissipation from batteries and battery systems. In JOSPEL, our aim is to reduce the energy which is used for the passenger comfort. And as a sub-goal, we also want to decrease the energy consumption of the battery system, but still enhance the life duration of the batteries. And we will do this for two different cars. The ones you can see here, one is from Alke and the other one from DOK-ING. So these are the project partners in the project, and these ones are involved in the battery system. We have here Alke and DOK-ING, the EV manufacturers, Atos, who is focusing on the data platform and data processing, CleanCap, who's an expert on battery management and the setup, and CDT and European Thermodynamics, who do the heating and cooling device we use for the battery system. Let's start with the basics. The lithium-ion battery cell is a galvanic cell. This means you can store electric energy in a form of electrochemic process that takes place in the battery. You can apply a potential across the battery cell, which forces a lithium ion from one side to the other one. And later you can use the stored energy if you connect both sides with an electric circuit, and then the lithium ion goes back into the cathode, and the corresponding electrode has to go through the electric circuit, and you can use it. Lithium-ion battery cells in particular have different advantages. So they have a high energy density, which is really important. They have no memory effect. They are rechargeable, so you can do the process in the one direction and also in the other direction. They have a long life expectancy and almost no self-discharging. The disadvantages are that they can be unsafe if not handled properly. So if there's a short circuit, they can really get hot and ignite, which is called thermal runaway. So you have to really be careful with these batteries and not overcharge it or deep discharge it or damage it in some other way. This means they are sensible in the operating conditions. So the main properties are the voltage that you can get from the battery and the electric current, so basically the electric power, and the capacity. So unfortunately, you can't draw energy from the battery limitless. At some point, the battery is empty. Here you can see, as an example, the charging process. So on this axis, we have the capacity, and here you can see the voltage, and on the other side, the current. So if we charge the battery, the voltage increases to some limit, and then we have to decrease the current and end the charging process. This is called constant current and constant voltage charging. And then when we want to use the energy again, we can discharge the battery. And as you can see here, the red curve, the voltage decreases, the capacity is then also decreased, and at some point the battery, we have to stop at some certain voltage again to protect the battery and do not deep discharge the battery. So basically this is the voltage limit within the voltage limits, the upper and the lower one, in which we can use the battery. And as you can see here, we have a higher voltage for the charging and the lower voltage for the discharging. This is due to the electric resistance of the battery cell, and this is also then increasing the voltage for charging and decreasing the voltage for discharging. And this is basically what represents the losses you have in this battery. So you don't have an ideal battery. You would have one if both of the charging and discharging voltages would be on the middle line you see here, which is the open circuit voltage, which is the voltage that the battery has when it's not operated. And there are also other different properties like the temperature influence. So all these properties are depending on the temperature and changing with the temperature, and also the aging. And of course, the batteries have different weights and different dimensions, which is what you can see here. Here you can see a lot of different battery cells, and there are basically three different main shapes. One is the cylindrical cells, you can see here. The other one is the prismatic cells, you can see here. And there's also these pouch-back battery cells. So these were the shapes. There are also different chemistries that are used for lithium-ion battery cells, which are lithium titanate, lithium iron phosphate, lithium nickel manganese cobalt, short NMC, lithium nickel cobalt aluminium, short NCA. They all have different different characteristics. As you can see here, this is some examples we got from the market research we did last year in the beginning of the JOSPEL project. And you can see here that the different cell chemistries have different energy densities. So NCA batteries have kind of high energy densities, and LTO cells have very low energy densities in general. And with the full cycles that you can do with this batteries, it looks like the other way around. So low full cycles with NCA batteries and higher ones with LTO or LFP, for example. And the same thing goes for the charge current. So LTO and LFP cells allow higher charge currents, whereas the discharge currents are more or less the same. Still, NCA batteries have a little smaller current rates for discharging. And as you may saw, there are a lot of different battery cells, and it's really hard to decide to go for a certain battery cell. So we did benefit analysis to find the perfect battery to use in the JOSPEL project. We started by looking at all these different properties of the battery. They were the decision criteria. We made a database of 49 different battery cells, and you saw them in the pictures earlier. We rated all the different criteria, and then we asked our project partner for a weighting. So we could, with this weighting, we could calculate one benefit value which represents the usefulness of the battery cell. Here you can see the weighting we got, and we listed then all the benefit values from the different cells, had a look at the top 5 batteries, and decided that we wanted to go for with the A123 20 amp pouch bag battery cell. So yeah, we decided to go with this battery cell, but obviously one battery cell isn't enough. It has a very low voltage and a limited capacity, so you need more battery cells. You have to put them in a row to get to a higher voltage. And still, you may want to put them also in parallel to get a higher capacity. And now we have a big energy storage, but we have to control it somehow and monitor it. Therefore, we need the battery management. So we start with putting a fuse at one end, maybe not just one end, but both ends and within the system, to make sure that the battery system stays safe and we don't have any too high currents. We have a battery management system, which is some device that can operate a main switch, that uses slave boards or measurement boards to monitor the voltages of all the battery cells, and not only the voltages but also the temperatures, and that also controls balancing system which makes sure that every cell in the system is at the same state of charge and there's no battery cell which is limiting the performance of the whole system. You have to do it for all the cells in the system, which is quite a lot. And You also want to measure the current of the system. You have to have an interface to the car so that the battery system can communicate to the rest of the vehicle, and the thermal management, which makes sure that the battery system stays at the temperature which is good for the system. So since we don't have any fancy photos of the JOSPEL battery system yet, because we're right in the middle of the project, I have some pictures of a previous system that Fraunhofer, ISE, and other Fraunhofer institutes made. So we also had a pouch bag battery cell. We made a stack out of these battery cells and used plates in between the battery cells. We were able to put some silicone oil through to cool and heat the battery system. These are the modules stacked together. Then the slave or measurement board to monitor the voltage and temperatures, and the whole system set together, and the BMS, which is communicating and processing all the different values. This battery system then was mounted in the concept car, and yeah, that's the assembly of a battery system. But hardware isn't everything. You also have to care about the software, and that's why I want to talk about stellar charge estimation first. So in a regular car, you have a fuel gauge, which is telling you the battery is full, the car is, the fuel level is sufficient, or you have to fuel up your car. In an electric car, it's a little bit different. There you have just some amps running from the battery cell into the motor, and you have the voltages. So it's kind of tricky. You have to use those values to get something close to the fuel level you have in a combustion engine car. And as you may already noticed, the voltage, for example, is changing with the capacity. So we can use that to estimate how much capacity or how much energy is left in our system. But since we have this electric resistance, which is increasing the voltage and decreasing the voltage with the current, we have to do an electrical model, which can look like this with different resistors and the voltage source, to calculate then with a statistical filter the state of charge of our system. The other method would be just amp counting. As you can see here, the capacity is nothing but the added up current we have. But if you add up the current, you also add up the error of your current measurement, and at some point your value won't represent the real system anymore. So you might want to combine those two methods, and this is also what we are going to do in JOSPEL. Unfortunately, also at some age, the batteries, the performance of the battery decreases. And these are the aging processes that take place in a battery. And as you can see, there are awful lot things that happen within the battery and decrease the capacity or the performance or both at different time rates. And since it's a lot, we generally test the battery cells. And here you can see a test we did with some Sony battery cells. And this is the normalized capacity. So we start with 100%. And you can see it over the equivalent full cycles. So we cycled the battery cells at different depth of discharges, around 50% state of charge. And we could see that there is a linear part of aging, and that at some point there's a very big decrease in the capacity that is left in the battery. And we did further investigate that, opened up the battery cells and had a look, and we could see that this is how the fresh graphite of the anode looks like. And in the first linear stage, it doesn't change. It still looks the same, but in the non-linear stage, or at the really big decrease of the capacity, you can see that there a surface layer gets built up, and which is basically causing then this huge loss. In JOSPEL, we want to investigate it too, because we really want to make sure that we're have a good system, and we want to know which causes this aging and how the rate of the aging is in for these battery cells. So we set up a lot of tests. We test pressure against unpressured battery cells, different currents, different temperatures, and different operating ranges. And as you can see here, this is some of the cycling tests we did. So the blue line represents 20-degree full operating range with 1 C charge and 1.5 C discharge. And the first thing that is really interesting for this battery cell is that if you reduce the upper limit a little bit to 95% depth of discharge, so not fully charge the battery, but leave 5% out of the battery, somehow the aging isn't as good anymore. You can see it in the green line. And also the batteries with lower discharge current seem to be aging faster than the ones with lower charge current, which was expected. But still, what is kind of interesting is that the battery cells which aren't cycled at a high current, like the red ones and the yellow ones, have a higher decrease regarding the capacity than the blue ones. But the blue ones, since they are cycled with a higher current, also not as much time passes as they are cycling. So we also check, of course, the calendaric aging, which you can see here. So here's the lost capacity due to just time passing, basically. So this is the capacity that is lost if they are just stored. So we put them at different state of charges. We put them at different in different climate chambers, which with 40-degree, 20-degree, and 0-degree. And this is the capacity loss we detected when we checked them. And to make it a little bit easier, we have here the results of the aging model we put in place. So this is just a function for which is depending on the temperature, the state of charge, and the time, and with an exponential which is lower than 1, so it's basically a square root function. And here you can really see why we didn't get better values for the 95% depth of discharge cells, because apparently there's some strange behavior, which is that the battery has higher aging or higher capacity loss when it's stored at 95%. But lower state of charges, like we assumed at the beginning, are causing lower capacity losses, and lower temperatures, like the green ones for 20 degree, have also lower capacity losses compared to the 40-degree ones, which are the red and the yellow ones. And 0 degree has the lowest capacity loss, since all these processes are depending on the temperature in a kind of Arrhenius law way. So now we discussed on the aging, and with this results we are making aging model for the battery cell we use. But as it's also important to have a look at the temperature, we also make a thermal model for the battery cells, which is based on this equation you can see here. So this is the equation for the heat generation. We have an irreversible heat part, which is the joule heat, and we have an irreversible part, which is the joule heat, and a reversible part, which is the entropic heat, based on the entropic coefficient of the battery cell. For the irreversible part, that can be calculated with an equivalent circuit we model for the battery cell. This can be used to investigate the internal resistance, and with the internal resistance and the current, we can calculate the irreversible heat due to the Joule effect. And the reversible part is a little bit more tricky. Therefore, we need not only the current and the temperature, but also this entropic coefficient, which we measured for the battery cells. And interestingly, it can be measured by just changing the ambient temperature and the temperature of the battery cell, and measuring how the voltage corresponds. And this is what we did here. So there's a dependency in the middle of the operating range, where there is also a dependency on whether you increase or decrease the temperature, but most of the time it's nearly the same. And it's also at some parts negative and at some parts positive. Negative means that if you have a positive current, this value gets negative and the battery is not heating but cooling. But most of the time, the entropic part of the heat equation is not the dominant one. But at very low current, it can happen, and at very low state of charge, that the battery is cooling itself, which is kind of interesting. We not only calculated this value, but also experimentally tested the battery cells. Therefore, we have the calorimeter you saw in the beginning. It has a measurement chamber, which is set in a big water bath, which is at a very stable temperature. And there are connections running into the measurement chamber, which allow us to operate the battery in this test chamber and measure all the heat which is going from the battery into the water, or from the water into the battery, with a measurement array. This way we're able to see how much energy goes in and or out of the battery. Here you can see, for example, one measurement. These are 2 discharge pulses with 20 amps at around 20 degrees Celsius. And here you can see on the blue line, which is the heat flux, or the heat that is measured, and by adding up those values, we also get the energy which was dissipated from the battery cell. And you can see here that for two following discharge pulses, we get very different energies that were dissipated, which is very interesting. And yeah, it basically shows that the heat generation is also very very dependent on the state of charge, and it's also very dependent on the temperature. And yeah, we can use this testing to verify the model. So now we have a lot of different models. We have one for the state of charge estimation, or the electric model, which is basically an equivalent circuit depending on the temperatures, the current or C rates, time, and the depth of discharge and state of charge. We have the aging model, which is yeah, a parameter driven model that is depending on the temperature, the current rate, the time, the depth of discharge, and also the state of charge, which is verified by the testing we do. We have the thermal model, and we need the EV model. So to put all those things together, we not only need the models for the battery, we also need the one for the EV system, which is basically has to tell us how high the currents are and which load is and which power is used in the car, and also how the car is connected to the thermal devices and to the environment. Therefore, we did some test drives. So the combination, so in the end, to do the battery management, we have to combine all these different models. Like the thermal model is increasing the heat, therefore the resistance is decreased, but for higher temperatures we have higher aging. So all these different things have to be combined and put into the EV model, and then we can calculate together with the battery management, which is giving us the temperature limits, the heating and cooling power, the operational management, which can be, for example, cooling the battery to have lower calendaric aging when the vehicle is plugged into the grid and we have energy we can use. And with these, we can compute the operational costs, the product lifetime, the eco balance or LCA, and evaluate it. And then, if needed, change some things and see how they are influencing these results. And then we can iterate this and do it over and over again till we have the perfect battery management system. And this is what we're about to do, or what we're doing at the moment in JOSPEL, to find the sweet spot in which we do use less energy for the battery management system, but still have a much longer lifetime for the battery cells we use. So that's it for now. Thanks for watching. You can stay tuned and have a look at our project website, and yeah, check it for more results and more interesting stuff on how to decrease the energy consumption for an electric car. Thank you very much. Have a nice day and goodbye.